Good morning, everyone. Welcome back. Welcome to those of you who are online and joining us for the first time today as well. If you weren't with us yesterday, I'm Annalise Riles, Executive Director of the Northwestern Roberta Buffett Institute for Global Affairs and Associate Provost for Global Affairs. And it's just a real pleasure to welcome you back to the second day of our conference, jointly sponsored with the University of Toronto, Roadmapping the Clean Energy Transition Dialogues at the Interface of Society, Culture, Science and Technology. If you're joining us just for the first time, this event launch marks the launch of a new partnership, the Toronto-Northwestern Decarbonization Alliance, and lots more to come about that. I'd like to just introduce today our colleague from Toronto who is going to lead today's session, Professor Dave Sinton, who is Professor and Canada Research Chair in the Department of Mechanical and Industrial Engineering at the University of Toronto. He's also the Academic Director of Climate Positive Energy, which is the University of Toronto's Centre for Interdisciplinary Research on Climate, and a co-organizer of this event and of hopefully all future work to come between Northwestern and Toronto. So Dave, over to you. Thank you.
Great. Thanks, Annalise, and special thanks to our Northwestern hosts. This has been amazing so far, and big hopes for today as well. I'm going to share just a few minutes of reflection on what we heard yesterday, and I won't cover much of it because we covered a lot of ground, and a few things that we can think about today, and then we'll introduce our keynote speaker. Emer started us off and really challenged us to think about culture and power in kilowatt units, and that we are power people. We're shaped more by our energy sources through history than likely through technology, even though those are of course coupled. But we're power people. We're mostly fossil fuel people. That's where we've come from, and that has deep cultural roots for us, and that was motivating and interesting and challenging. And I will share, if you're looking for a quick definition of liberalism, Emer's not your guy. Okay, don't pursue that. But I really appreciated his framing of it, and also the thinking about the communication, the invisibility of energy. And I feel engineers have a bit of responsibility in that, right? Cars, when you drive in a lovely vehicle, it's so comfortable and quiet. You're not presented with the realities of the burning inferno and the explosions that are taking place. You know, we've covered all that up for best of intentions, but we've hidden energy so well. And Emer, I loved your bills example, Canadian currency, and the picture of the refinery on the early 10, and it reminded me that we hide energy even more than we used to. I mean, you can decide whether you like a refinery or not, but there was an honesty in that, in what we were doing and what we are doing. But the new bill also fits Northwestern color schemes now, so it's better. Kim reminded us of why we do these things, of people, and how to bridge and work with communities and individuals, and also for me really reminded us of the challenge of it, the importance of that, of course, but also the challenge in that. And we had some great discussion, and Marianne put it to the group, how do we change based on what we've learned from Kim? And I think then I got a little bit sad, and I'll tell you why. It's because from an engineering perspective, when you hear about the delays, and Kim gave the example and others did later in the day, about how it doesn't line up with the tenure clock. When you're doing community research, it doesn't line up with the tenure clock, it takes longer. I'm sympathetic, of course, to tenure clocks. But the larger challenge, the 2050 deadline, it's worse than a tenure clock, right? So, in an engineering perspective, I can't help that. It's deep within me, says this stuff don't scale. How do we do that in time, given that? So that's a real challenge. But then I had a Danish and one of those barista coffees, and I felt I felt a lot better, in part because a discussion came up with Michael and Jennifer. An idea emerged and also from Kim, that not all of us need to be social scientists, and not all social scientists need to be engineers, scientists. Rather, we can think of it almost as a clearinghouse model, where we get that insight that we need to steer our technologies without necessarily being the people that necessarily connect the communities. I thought that was very useful. Last couple things, a couple big themes that came up that were new for me yesterday. One was this problem space and solution space. Folks that think about the problem all the time, folks that people that think of the solution all the time, and the importance of crossing that border in addition to our international border. I love that, Annalise. The other one was the could, shoulds, and the woulds. We talked, the engineers are the coulds, and the scientists are the coulds, what could happen. The social scientists, the shoulds, what should happen, right? And then we were reminded by Megan, I'm not sure if she's here now, that the woulds, right? Is there an economic driver for this? The coulds can make it happen. The shoulds can decide what should happen, but the woulds, the economics, the business piece needs to be there as well. And last thing is the pragmatism that I thought was in all our discussions yesterday and today in terms of what next steps can we do, what concrete next things can we do. I thought that was very helpful and inspiring, and hopefully we get there. Great. Let's go to our first keynote of the day. It gives me great pleasure to introduce Patty Romero-Lenko. We're delighted to have recruited her to U of T. She works at the interface of people and communities and climate, and particularly in the context of cities. And Patty's had a history of working in Mexico City, in LA. She's going to tell you about some of that work today. And you can guess the next stop is Toronto, and maybe with a side of Hamilton. We're trying to convince her as well. She's a new U of T CERC. What are those? Those are Canada Excellence Research Chairs. It's money we use to recruit top talent internationally, generally. So we look out over the world for experts that we want to recruit in a specific area, give them lots of funding, and we were fortunate to attract Patty. We know that Northwestern would never look internationally to recruit a top faculty candidate, but U of T does that sort of thing. And lastly, I'll add Patty's got a long CV, and I won't review it here for you, but I really appreciate that Patty, from her long time at NREL, speaks engineer, so she can really cross the border. So Patty, so happy to have you here. Thank you.
Well, I need to say that when I was asked to apply for this position, I didn't have a clue of what a CERC is. And only when I got it, people told me, this is really something good. And I was like, I'm glad I didn't know before, because I am always so like, oh, I'm glad I didn't know it happened. And now I just hope to enjoy what this is about. Okay, guys. Karen already told us yesterday that cities are key players in the climate change and the energy and the water arenas, not only because they concentrate populations, infrastructures, and problems, right? They are source of 70% of the energy use worldwide. And give and take, the engineers could tell me, they emit between 60-something and 70-something of the greenhouse gases. The most important thing, and something that has driven me all my life, is that cities are sources of solutions. It is there where we have universities, artists, you name it. And that's, I mean, this tension between being the source of the problem and the solution is what has driven me during the last years to work with cities and city actors. That said, I mean, although cities hold a huge potential to help us navigate, city actors, right, the challenges we face, the extent to which current practice can address root causes and links between unequal urban development and climate change is limited. So with this in mind, and it's limited because, and that's, I will show you how I address this issue of the problem and solution space, because either we work on one sector or we work on solutions or on problems. We don't know how to connect things. And it's not because we are bad intended, it's because our nature, and that's something that an economist studied, we tend to fragment the reality and to focus on little pieces and bits because we cannot deal with the whole enchilada. So we need to say, okay, how do I get a piece of it? Okay, what I will do today is that to share with you lessons from what LA 100 equity strategies did to foster equity in sustainable transitions. I hope I can. So in 2019, the Department of Water and Energy of Los Angeles, also known as LADWP, asked NRAL, my ex-lab, but we still will be right, working with the lab, to conduct a study to explore the feasibility, the technical feasibility of transitioning to 100% renewable energy. So what happened is that the lab found that it is feasible and that we can, or the city of Los Angeles can achieve a 100% reliable renewable energy systems if they couple this with the electrification of key sectors, particularly transportation, which we know is the one that will offer us the most out of our investments, right, to decarbonize our economies. And they also found that this effort will provide the city and its population with significant greenhouse gas, air quality, and public health benefits. That said, while this is possible, while it is possible for all Angelinos to benefit from these model LA 100 clean energy scenarios, they also found, and this was also the result of pressure, guys. I mean, these things don't come for free, okay? They found that improving equity in participation and outcomes requires intentionally designed equity strategies. And I can tell you, historically, inequities happen because of policy decisions, because of policies and practices. They don't happen because God came and put inequities there. No, it's action what creates this. And then action, like the chicken and egg thing, right, creates structures that reinforce action and vice versa, right? So in this context, in 2021, I was approached to lead the social science component of what became LA 100 equity strategies. And I remember when I was approached, I said, I'm not gonna be your input, your afterthought. I'm not doing this. I'm not gonna lead this project. And the lady told me, no, Patty, we are serious. We really want that you do good social science. And yeah, indeed, I did not only, I hope I did good social science, I learned a lot from this project. So the goal of this project was to ensure that the Los Angeles transition to 100% clean energy also improves energy equity. And let me just give you a sense of what challenges this city, which is one of the pioneers, the front runners in whatever you can imagine. Call it climate, call it adaptation, call it, you name it. And California is another leader worldwide. So, but the challenges are huge. One of those is that this 100% transition requires bringing everyone along, and decision makers are not used to bringing everyone along. It's not in their nature. And engineers even don't know how to deal with people. They know how to deal with models and with optimization, right? And that's terrible because this county, Los Angeles, is home to 30% of the state's impoverished population. I could say is home to more, but give and take, those are the numbers. The current energy system in LA and in many cities worldwide is quite inequitable. Why? Because marginalized, disadvantaged communities experience more burdens and fewer benefits of energy. So this means that an equitable transition will require a major shift in how investments and programs are allocated. But not everything is easy in life. And the LADWP, which is a public utility, is faced with huge constraints. Why? Because the transition will require increases in rates. There is no way around it. But these increases, and that's what some colleagues of mine already model, will result in or will affect more the poor, the marginalized. The moment utility wants to increase rates and say, hey, and we want to benefit these people, they will be faced with two propositions. One of those is 26, which were promoted by key big players to say, you don't increase these things because those are taxes on us. And they won the mobilization. So for the city to change or for the utility to be able to increase fees, they will need to get in a coalition building process to be allowed to increase those and to create a proposition that overcomes the other propositions. So we all are very happy saying, whoa, we need to change the world, but there are constraints. You know, there are political and legislative constraints. And of course, as I was saying, equity requires community processes. So what we did? And this is the plan that my then postdoc and I put together. We were the only two social scientists in a group of 30-something people. First in equity, right? First reflection for whatever we do here, guys. Give equal money and decision-making power to key disciplines involved in any project. There is no discipline that is better than the others. But okay, here we are, we embark on creating this, and our goal was to really operationalize the principles of equity that Kim already referred to yesterday. I will refer to them again today. So as you can see here, you see we decided that there would need to be a continuous engagement with communities, not with their CBOs, with the underserved groups that we are all talking about. We created, or LADWP, based on our advice, created a steering committee with 14 CBOs to steer the process, to make sure equity considerations are centered in their efforts, an advisory committee to advise on the feasibility, technical and political feasibility of whatever we suggested, and the 6 groups of modelers who could work on what was called the technical scope. Here below, you see the phases, etc. So a couple of reflections on this. This looks great in paper, but it was hard to implement. Why? Because of organizational inertias. The LADWP was really concerned that 2 social scientists could go and talk with people, so they sent a chaperone to be with us, interviewing people, etc. I felt like the quinceañera in Mexico. I was always with my chaperone, who was an amazing lady, by the way. So the engagement process was delayed because the utility wanted to have everything organized and in place, and that resulted in the modelers not being able to get the input they needed to do their work. Another key lesson learned, guys, we want to engage, and these kind of projects require engagement. We want to engage with communities. We need to open like 4-6 months for engagement to inform the scoping of the project, and then start the project. And then of course, our organization had also inertias. It was just so hard for them to understand that we needed to engage with communities. Well, we need our models. I said, but we are talking about equity here. How do you want to model what you have no idea of, what priorities, etc. Okay, so these are the 17 chapters we produced. The first 4 on top were coordinated, facilitated, led by me. The ones in the middle, 8 were led by the modelers. We informed their efforts. And with some of them, we really got in good relationships, understanding how important it was to have the different expertises to bear on the issues they were addressing. But you will notice part 3 that was led by UCLA. No matter how hard we tried to say, hey guys, we need to engage. We are in this together. UCLA, for reasons that are hard to explain, decided to go by their way. So key lesson learned, you want to engage, you really need to make sure every party involved agrees on 1 or 2 questions they care about. Otherwise, just don't dare to start any process. And I'm saying that because I saw that everyone is so enthusiastic about our work, about what we will do, which is very amazing. So, but let's just learn the lessons, okay? Now let me go quickly to the goals from my perspective, right? Because I was not allowed to really engage in the iteration that is needed for us to really be on the same page. But that's another story. I mean, I always say, we want to change the world, guys. Let's start by changing ourselves and the way we do business. The day we are able to challenge ourselves, that day we will be able to go and say, hey, I beg for you to change, right? So, but that was another lesson. Let me then move to the goals of the social scientists. We use mixed methods to examine community values and understandings of problems and solutions. Those were the three questions that we used to guide all our efforts, because we needed to inform way too many projects, to operationalize three tenets of justice, and I'm glad that Kim already referred to them, and to develop options for energy equity strategy development. So we connected the problem and the solution space. Those are some the locations of the listening sessions, which are focus groups, but communities hate the word focus groups. They feel that we are like exploring them, and you need to be careful with what words would you use even to do these things. Many of the listening sessions were held virtually. That's why you don't see all the, we held a total of 15 listening sessions. This is how we frame our approach to the three tenets of justice. And if you are interested, I already will share this paper with Ted. We have a paper we publish on this. For us, procedural justice is not only about understanding why communities are not being heard, but it's about making sure they are key players in the co-production of knowledge. But that is not enough, because communities, it's not that equity lands there and then we are faced with problems. Inequities are built over time. History matters. And that's why we also operationalize recognition justice in order to understand and address the legacies of past and current practices that result in the energy inequities communities face today. In our understanding, without engaging with these two relational aspects of equity, it's impossible to ensure a just and equitable distribution of benefits and impacts, or a more just, right? I don't know, I'm more and more convinced that the most we can dare to achieve is improvements in equity. I don't know whether equity will be achievable as a big thing. It's perhaps like democracy and love and happiness, right? I always want to be happy, but I cannot always be happy, right? The same is with equity. We want to be more equitable, but I mean, Okay, and this is our overarching analytic approach. As you can see to the left of your screen, what we did with chapter 1 was to review literature, official documents, etc., to understand the legacies of redlining, of investment, of location or seating of infrastructure, etc., and how they now bear on the factors influencing current inequities. That's recognition justice. And we learned a lot. For instance, many of the red line communities in LA, and I learned also in other cities, are the ones that are more likely to suffer from the health impacts of urban heat islands, air pollution, heat waves, etc. They are more likely to live along transportation corridors. They are more likely to live in areas that have huge neglect and lack of investments. And I think that's also the case in Toronto. I mean, I just have been doing some walking transits, and I'm like, that might help us there. Okay, and then you will see to the right, I was able to connect the problem and the solution space. That's the only thing I'm proud of, right? Why? Because what we did was, when working with communities, was asking 3 simple questions. We show all the beautiful things saying, this is what the city wants to see in the future. And we just ask them, hey, tell me, how do you see your community in the future? What do you dream about? What do you want your kids to enjoy? And that immediately turned them on to say, well, I would like to have A, B, and C, for instance, green areas. But guess what? These and these and these problems are my concern. And we always make sure to ask, and what do you suggest to address those? So that understanding and a coding, transcription, coding, etc., of the narratives that emerge from that allow us to create our understanding of the problem space and the solution space. You also will see that the political context, meaning the organizational structure of LADWP and other city of offices, and also the legislation, etc., are key in our analysis of the solution space. We are also working with goals, with desires, with aspirations, and we elicited the values of communities. That's key. What do you want in life? Well, I even do it with my colleagues, right? First question I ask, tell me about your values, right? Because I want to understand what values move them to do things. Okay, so that's, and we also are using metrics to measure things. But we are suggesting in our work metrics that are informed by communities. So these are the methods again. Let me just read to you some of the quotes that represent the recurrence, what we call in the parlance of qualitative analysis, saturation, right? This is a beautiful quote that many community members share. This is an ethical principle. This person, an amazing lady, she was so strong to us. She was saying, you guys are extracting information from us. I was like, we are not, but yeah, I understand where you come from, right? She said, the very definition of equity, which we spent a lot of time talking about, and even now, those of us who have been disadvantaged are sometimes uncomfortable with, means it's not about how much. It means that we've all made a commitment that until we, the disadvantaged, catch up, nobody else gets anything. So more and more of it becomes ours because we have been inequitably treated. But what we want to know is how is it proceeding? So this person is acknowledging that, or telling us this is the value that we want you to use to guide your decision-making process. Okay, quickly, I will share some highlights of findings, and you won't be surprised by them, by the way, but well, you know, the problem is what do we do about this, right? The benefits, we were asked to do an analysis of the programs and investments of the utility, and we found, not surprisingly, that the benefits of these programs and investments are unequitably distributed. For instance, you see here in the middle the programs, and then to the right, you see how we did all the analysis of the total of money invested, which is in green, the average amount per customer and percentage of incentives. But the bottom line for you is that programs such as the solar net energy metering, the residential EV incentive, which are the programs of the transition, right? These are the energy transition programs, right? These proportionally benefited households in non-disadvantaged, mostly white, not Hispanic, owner-occupied, affluent neighborhoods. You would wonder, why so much wording? Because the utility cannot speak about race as a key determinant of inequities. The same is with the federal government. They cannot use race as an indicator of inequity. Why? Because they can be sued, and then they cannot do what they need to do. Again, the political context is something we need to analyze, right? We also found that the low-income and lifeline programs provided subsidies to disadvantaged communities as designed, but the point is, most of the monies go to the wealthy. That's the bottom line, guys. you want to know where the will is, ask where the monies go. And then you will have a good answer, right? And we also found in terms of the grid, Dave, you were mentioning the grid yesterday, the grid is really key. For me, the grid is like the bones without which it's hard to make sure, or the circulation system, right? It's hard to make sure that blood comes to, the cells, et cetera, et cetera. But okay, we also found that disadvantaged communities and mostly Hispanic communities experience more power interruptions. And the communities told us, talking about they don't know what is going on, they know. They were like, we suffer a lot of these, interruptions. Oh, I don't know what I did, but okay. So in short, we found, and I cannot share with you all the data, right? But we found that underserved communities face higher energy, housing, and transportation burdens, unsafe temperatures, and are more likely. And I'm saying are more likely because I know that epidemiologists always tell me, Patty, be careful, they are more likely. You cannot say that they are, because the burden of disease is a result of many compounding stressors. So we are just analyzing one of those, that's why. Okay. These inequities, and that's the point, and that's why history matters. It's a pity that Keith is not here to show him, yes, how much I care about history. These inequities result from historic legacies of infrastructure ceiling, lending, redlining, disinvestment, and neglect. Talking about what communities know, this is a beautiful quote that, confirms, grounds, right? Ground truths what we are finding. This person says, while I appreciate raising the concern about addressing current infrastructure, ensuring up that infrastructure is, I don't know, right, okay. I also wonder, does our infrastructure have the capacity to deal with these things? There is a sense of neglect, and that's something we hear over and over again. In terms of the outdated infrastructure that needs remediation, I'm hearing discussions about what we are going to do to fix, improve the infrastructure to make way for new. But how are we going to remediate the old? And I think that's also about building trust in the community, right? This person is referring not only to the hard infrastructures, but the soft infrastructures, right? Which is something we found. There is something that a lot that could be done just by doing a better job engaging with communities, right? What is the plan to remediate some of the things that currently are causing damage and have been causing damage for quite some time now? Okay, and again, I mean, just in summary, right, communities are telling us, in terms of their lived experience, that they are faced with poor quality and maintenance of infrastructure and housing. So that if we want to get all these new technologies, we need to work with the roofs, the electric panels, guys, they cost a lot to change. We're talking about around 10,000, right? There would be, it could be more or less, right? A lack of affordable housing and also a lack of affordable transportation. And the renter and owner issue, which is a huge issue everywhere I go to. Toronto is also facing that, right? They are also facing lots of barriers to making energy decisions for themselves and their community. I remember we were asking in one meeting, in one listening session, hey guys, what do you think about all these programs? What program would you like? And one guy raised a hand and said, but if we don't want fish, we want to learn to fish. We want good jobs. They call them the high road jobs. And that's why in our CERC, I will be working with the minister over there on jobs and workforce development, because people say, don't give me programs and subsidies, give me good jobs, train me, give me the possibility to pursue my life with dignity. And they also face a lack of access to financial capital to do everything you can imagine. There's a lot of mistrust and grievances related to how policies and government agencies work. Let me now quickly share with you three key issues, codes, we call them, right, that emerge and as recurrent concerns for communities. The first was self-determination. And we didn't call it empowerment, right? Which is not only about subsidized opportunities and benefits, it's also access to high road and well-paid jobs, training and entrepreneurship in their communities. They also need support to access to the programs. The issue of eligibility criteria is key here. Many poor to middle income households feel that they are not poor enough to receive supports, but they don't have the money to pay for things, right? They are saying, choose other ways to help us, and they need usable information. And I think that's where we can create and mobilize knowledge to support them. The universities have a huge role to play. To close, because I'm almost there, we developed some options and we came up with 12 strategies and came up also with building blocks that could help the utility know where to start. And here are the criteria. Let me just share with you the equity strategies. I decided to organize these strategies in blocks. On the left, you see the ones that are beyond the purview of the utility, but are key for the success of the transition. Communities ask over and over again, improve city regulations, accountability, and enforcement. They are dealing with predators and that say, oh, we represent the utility, and just trick them. To the middle, you see something I think we also as research need to work on. In the middle, this collaborative platform whereby instead of just coming and doing our project, if we are decision makers, or our research, if we are researchers, we do that and we disappear. What they want is a continuous engagement. And they also want to be part of the program and service co-development efforts, part of efforts to improve transparency and continuity. Only by having those backbones will it be possible to deal with three other concerns. One is from the top to the bottom on the right, to have tailored training and high road jobs, to be able to manage their bills and deal with their debts. In the middle are the programs that address recognition justice issues and are mostly concerned with investments, capital, efforts for them to improve the quality of their houses, transportation, you name it. And to the top is what we call community voice and resilience. And they really offer many solutions, such as community science. They say, we can do science. Why only you guys? Who told you that you are only the good ones? And they offer good solutions. And they said, it would be good if you work through trusted messengers. In this case, the trusted messengers were the promotoras de salud. In English, the health promoters. And let me tell you, I ran most of these listening sessions in Spanish. We always offer them, what do you want to use? And mostly they like Spanish, which was a pleasure for me. Okay, with this I close, and thank you for allowing me to share with you this.
Microphones here. All right. And water. Thanks so much, Patty. It was excellent. So we've heard a lot there, and there's likely some questions. So let's go to the audience. Here's a line here.
Revealing my background as an emeritus engineer here, but there are a lot of problems like rolling blackouts that utilities have to take into account and have plans for what neighborhoods go first and for how long. I was wondering if that comes into your study, and are disadvantaged neighborhoods disadvantaged as far as rolling blackouts as well?
Yes, that came, and when it came to that and other issues, communities always say, just go to Hollywood, just go to the west side of the city, and you will see that the infrastructure is underground, that they don't face so many blackouts. And we did the analysis showing that they face more blackouts than other communities. And the utility, it will be hard for a utility to do something to the wealthy because they mobilize, they are organized. So there are many inequities playing out there. Yeah. Great question. Thank you.
And that strikes me as one that's very easily trackable, right? Is where were the brownouts, and a policy could address that one. It's a great point. In some ways, it's one of the easier ones that could be addressed, right? Lower hanging fruit. Go ahead.
In the solutions side, have you looked at more like trust models or cooperative models? Because a lot of your solutions are still based on an individual qualifying for financial investment, whereas these communities often work together, and yet the financial models are not there to support them. So they take over their own neighborhood energy source.
Oh, thank you. I mean, second great question. Yes, we look for ways for communities to get their community abilities to act taken care of. One of those efforts was the community science. There is also working with trusted messengers. And they also suggest that was in the middle. I mean, I couldn't share the quotes, right? That's always what limits what I could tell you. But they also said we could create community boards to hold them accountable. So they suggested many actions that we turn into strategies. The bad news is that in the presentations that are underway, the utility decided that they know what to do there and that they don't need communities to tell them what to do. So it's part of how we need to change the cultures, but those are great points that we incorporated. Thank you.
Yeah, thanks, Patty, very much. I really appreciated how you, at the end, summarized sort of that triple burden of, material deprivation, environmental exposures, right, air quality and noise and temperature, and transportation poverty, which is really nice, very well said, right? There are a lot of people who just can't make it to the job interview because there's no transportation there. Then you said that this is legacy, this is historical, this is planning, this is policy. But that legacy is still getting perpetuated. And we actually see this, and Karen talked about it in Toronto, where the way we're thinking about how we develop our cities, welcome new in-migration, build housing, is actually perpetuating all of these things. So this is as much, a planning issue as it is social and economics.
Yeah, and a lesson I learned, and that's why I want to continue working with LA as one of the use cases, and also because I want to bring back to them, and I was not allowed, That's where you learn that as scientists as you are not allowed, right? But in the case of transportation, I think that we need to work on a couple of fronts. One is mobilization and coalition building. Without that, the ones on top won't listen. That's clear. The other is social innovation and entrepreneurship and showing that this is possible, And I think that on the two fronts, we can work as universities with communities. And the other is, particularly for transportation, many communities, there were these debates between the pro-car and the pro-transit community members. And I think that those debates offer opportunities to change the paradigm and to say, no, we want public transportation, or we want something, because private cars are not taking us away from anything, no matter how electrified they are. But I think that you are right. We need to work on the different fronts, and there are different sources of innovation that we can scale to affect more structural change. We need to work on that. That's what I'm sensing.
Another question here. Go ahead.
Thank you. How do you know you're actually talking to the community? And the word community has reverberated throughout the whole discourse. And I I've personally experienced in my research where, it's like, oh, you need to return your data to the community. You need to, but the people who step forward often as leaders of the community are empowered and have captured capital and various things. So how did you, in this initiative, reach the community, and how are you defining the community?
Right. What we did was mapping exercise, and we worked through two ways. One was to identify using quantitative data where the more disadvantaged communities were, and also using a literature review. And then we also used a strategic snowball approach to reach to CBOs. In my prior work, I agree with you. I found exactly what you are saying, and I still found it here, that not all CBOs work with grassroots, right? Some are more citywide, some are more national-wide. So I can tell you in honesty that we were able to, like 0.5% of the people we work with were members of disadvantaged communities. The other half were leaders, grassroots leaders of disadvantaged communities, and you could see it in their discourse, the narrative. So yes, I try to do my best. I am aware that there are power dynamics, and I could do a reading of them, but I didn't come here to talk about that. But yeah, good point. And you do what you do, and you do what you can do, and what you cannot do, you don't do. Remember that? Pray, God, teach me how to understand the world, and whenever I cannot change it, I learned that the hard way, right? It's true, yeah. Thank you.
Great, we're at stop time. I'm
Oh.
sorry, we'll have to catch you another time, or good news at the break. I think you'll be busy at the break and maybe over lunch too.
Nice. You rock. What series of questions? I will go back home. I will ask Kim, tell me. Okay, thank you.
Well, I think they're just getting started, Patty. So let's thank Patty again. Great. Great. So for those of you who are wondering, who are these scientists and engineers? Our keynotes have been from the social sciences and humanities side so far. We're delighted to have maybe the best representation we could have here in Cecina. Cecina's got a long, distinguished academic career, starting MIT and UC Berkeley, and then postdoctoral work at Max Planck Institute, and now at Northwestern University, and is really leading in hydrogen, and it's such an important technology, also a bridge from electricity to storage and to fuels and to industry. And Cecina also leads an important center here in hydrogen at the Northwestern University. So we're fortunate to hear from her. Please come up.
I'm slightly concerned that I copied the wrong slide, but hopefully what shows up next is the right set. Okay, pleasure to be here with you, and very much on the science and technology side of things. So we've heard a lot about the social science and the humanities and so on. So this is very much in the other direction. But just to remind ourselves all of why we care. Just to, and then it's not. There are certainly energy inequities, but there's also the aspect that our planet is not going to survive much longer unless we really address this issue. And so, the latest UN climate report was actually published in April 2022, but it wasn't disseminated until earlier this year, and saying, look, it really is now or never. July 2023 being the hottest month on record. And where my siblings live in New York City, I panicked and called my sister, are you okay? Because she's in Brooklyn, but she's fine. So the good news is that we actually have a lot of non-fossil resources to use that can supply the world. And if we look at our global energy demand, this is a few years old, but still, we've grown, but not tremendously. This is on a log scale. that we see that solar is 20 times the amount that we use. And even all these other resources, geothermal, hydropower, ocean, wind, these are all really significant in the quantity relative to how much we use. So there is good news ahead of us. And then there are all these hopeful trends and projections. This is the US energy consumption by fuel. And as has been talked about, unfortunately, petroleum and natural gas are not declining as they should. The good news is that renewables are increasing. Hydro is basically staying flat in the US because we've put in as many hydropower plants as is reasonable. And coal is, declining. It's interesting to see that the recent history has been a strong decline, but the projections are that it's not going to really decline much further. One thing I want to point out on this projection is that you can see that the point at which renewables exceed coal in terms of the US primary energy source is here about almost today. So this is a prediction from 2021. These are done every 2 years, so I haven't gotten the most recent one yet. And I have these, downloaded on my computer. So I said, what was predicted in 2019? The prediction in 2019 for this crossover point was way out there. And so it's just, important for us to recognize that we make this future. We don't just accept these predictions as they are, that we do all the hard work, whether it's the technology development, it's the policy pushing, it's the, informing the community and society about the importance of these issues, or even our daily choices, that we can, in 2 years' time, make a 15-year change in these predictions. Okay, so certainly rising public demand and declining technology costs. So here is that issue that I raised yesterday about how solar PV has come down 90% in costs in a decade. That's really remarkable. Of course, solar PV photovoltaics has been under development since the 70s. And yes, people would have liked to have employed it then, but it was far too costly for anyone but the super rich to really be thinking about it as sort of a luxury. But now, new power generation in the US, it is cheaper to do that with wind and solar than even natural gas, let alone coal. And energy storage with batteries, this is the lithium batteries basically for electric vehicles, that has also come down by 90% in a decade and is now, almost, but still the electric cars are still more expensive than combustion cars on average, but it is approaching there. Now, if we want to think about decarbonization overall, we need to have enough storage to back up those sources of wind and solar, and even hydro. So we recognize many times that these renewable resources are intermittent, but in fact, our use of coal and nuclear, these are steady state sources, and our consumption is actually not steady state either. So really the only source that can go up and down is coal. But if we had better batteries, we could really make use of our renewable resources. And in fact, that would be benefits for coal and nuclear, but we don't want to benefit coal. Okay, so where are we in terms of battery storage? So a long way to go. So here's where batteries are. So most of the world's storage is really inherent to hydro, right? So we all know that there's a lot of storage there. So this dwarfs the electrochemical, which is batteries. So here's batteries, around 2 gigawatts capacity, rated capacity. Now, I don't know how many hours this would be. So this is in power, not in energy. But if we compare this 2 gigawatts worldwide to the US installed electric power capacity, that's a terawatt, that's 500 times more. That's the grid capacity in the US compared to all battery storage in the world. So yeah, long way to go, long way to go. So you can think about some sustainable energy cycles, use these beautiful carbon-free resources, and think, oh, I would like to do battery storage, deliver that in the developed world, at least through an existing infrastructure, and then utilize it with no waste products at that point. So this is a beautiful scenario, and as I said, that's great. This has improved a lot because of the cost declines. Delivery certainly exists. We have to worry about outages and so on in underserved communities, but for the most part in the US, in the developed world, that exists. Utilization depends if you need batteries for a vehicle, but if you're using it in a stationary application, certainly we can do that. All right, so this is the problem, as I said, the battery storage. So you say, all right, let me change that and use some sort of fuel, which might be a liquid organic. Okay, so that might be another strategy. Okay, if I do that, then I have to change that for pipelines. Okay, and if I'm going to be delivering fuel, well, most use of a fuel is not direct. I have to have a way to convert that fuel to electric power. So that is another challenge. And if I want to do that in high efficiency and no pollutants, I would probably use a fuel cell. I'll describe that in a moment. But if I'm using an organic liquid here, I have to have inputs to make that using my resources. And again, if it's a liquid fuel, it's probably going to be water and carbon dioxide. Okay? And that means that my products here, when I use that liquid fuel, will be water and carbon dioxide. And if I want to use this strategy, I have to have in place an idea of how I do the CO2 recapture and delivery. So if I'm going to use this part of the cycle, I have to think about that other part as well. Because if I'm taking carbon dioxide and releasing it to the atmosphere, that's not really helping me if I had a concentrated carbon dioxide source. All right, so you say, well, let me change this and think about using hydrogen instead. Okay? Because that way, I don't have to have a recycling strategy. I use water as my input, and I have just water as my output. That's great. That's an abundant reagent, and I have zero emissions. Good, great news. And so the US Department of Energy announced its Earthshot program. This has now been a couple of years ago, so September 2021. And the idea was $1 a kilogram hydrogen in a decade. We've already spent 2 of those years of that decade, and we still have, unfortunately, some way to go. And the real challenge here is the storage. This is really hard. And the delivery is very costly because we don't exactly have a hydrogen delivery infrastructure. We have a liquid fuel delivery infrastructure. And so as part of the all this incredible legislature that went through in the Biden administration, the plan was $2.9 billion for Clean Hydrogen Initiative. Of that, I think it's around $8.5 billion is explicitly for the infrastructure, and only maybe $1 billion for the research and technology developments. Okay, so you might say, well, oh, this is really hard. This infrastructure is really, really expensive. Maybe I can change this around where I do storage and where I do delivery. Okay, so that might be a solution. And if you do that, you say, okay, if I now do the delivery through electricity, that's my picture now, I will be able to deliver electricity and use that in, let me do my storage, my animation wasn't exactly correct, but here's the storage that I want to do now, which is to take the electricity and make hydrogen. So I can do that remotely because I have an existing infrastructure. I can exploit that. I don't need to create a hydrogen delivery infrastructure, and I can more locally use hydrogen to store my energy. And if I have this cell, which was operating as a fuel cell before, but I can make it operate reversibly like a battery, but more scalable in terms of overall size, then I can do my storage remotely. Okay? And so I need to have high efficiency and zero emissions for this reversible cell, which is not the same thing as a fuel cell. All right, so that's one strategy. Another, so let me just talk about electrolysis. Hopefully not too technical. So basically electrolysis means that we're going to take water and split it, okay? And we're going to use electricity. It's energetically, this is downhill. So that means you have to put energy in to make it work. And I've actually done this little demo. It's really quite easy. You can have an aqueous solution. So you put in a little bit of acid in that to get you some protons, and you link up a little battery to it, and you drive the protons from one side to the other. And you do this hydrogen evolution reaction on one side and oxygen evolution reaction on the other side, just because you have the energy potential of that battery, and you have some minimum voltage that you know that you need because of the because it's downhill. You know exactly how much you have to input to overcome that. Oops. And you create these bubbles of hydrogen and oxygen, and maybe you want to put in a diaphragm so that hydrogen and oxygen don't just come back together and blow up. Okay, so good. That's our reactions, so there they are. And I would call this a solvable challenge. I mean, it's not easy, and there are plenty of people who are doing work in this area. Ted, I'm sure, you know, and in my laboratory as well. But it is not impossible. And because of the fact that the solar and wind electricity have come down so much in price, this is a much more reasonable thing to do than it was a decade ago. A decade ago, this would have been insane because solar electricity was way, way, way too precious. You would never use green electrons to do this. But now it makes sense because you've got, you know, extra resources that are sometimes producing electricity when we don't even have anything else to do with them. Now we have to put that in the context of hydrogen production and use today. This is mostly predictions, so you know how I feel about predictions. So here is the point of approximately where we are today. Most of global production of hydrogen relies on fossil fuel. So maybe, you know, 5%, I think even 90% might be an underestimate of how much fossil fuel goes into the hydrogen production. And it's through these reactions here of natural gas or coal with steam to give you hydrogen and then CO2 as the product. That is, you know, that's how it's done today. It's not done by electrolysis. And what's interesting also to keep in mind is that the annual demand for hydrogen has nothing to do with you know, green sustainability and preventing carbon emissions. It's actually goes primarily into oil refining. So that's the biggest part right here. And methanol production is right here. And this in mixture, I believe that's also in oil refining because you don't have to have it be pure hydrogen in order to do oil refining. So these two, that's where it gets used. That's where hydrogen is used. So that is something to keep in mind when we talk about the hydrogen infrastructure. And when I hear oil companies being very enthusiastic about the hydrogen infrastructure, I get very nervous. So, you know, hydrogen is also a challenge, as I mentioned, for storing. If you look at how much energy it carries per gram, it is awesome, right? It is way more than diesel fuel, gasoline, methanol, but that's just the hydrogen molecules themselves. We have, you know, it's a gas. So if you put it at 1 atmosphere pressure per liter, it doesn't have very much because there's not going to be very many molecules of hydrogen in that liter of, you know, that tank that you've created unless you put it under high pressure. So the energy content that we're describing here is the enthalpy of this reaction. So how much heat is produced when you burn these fuels. Whoops, and I keep doing that one. Okay, so, and just a mnemonic, just if anybody likes to have these mnemonics, a kilogram of hydrogen is about the same energy content is a gallon of gasoline. Just a way to remember. So because of the need to have hydrogen at high pressure, these are the typical tanks that are used. So it's a carbon fiber composite that allows you to have the hydrogen as high pressure. So it carries about 5.5 kilograms on the Toyota Mirai using this kind of a tank, and it's at 10,000 PSI, which is 700 bars. So that means 700 times the pressure of atmosphere. And there's about a 15% penalty for that compression. Maybe it's not so huge, but it's non-negligible. And I think that, you know, as car companies are trying to decide whether they're doing hydrogen fuel cells or batteries, one of the things is that the range is still higher for the hydrogen fuel cell than it is for the battery, and the recharge time, it's 5 minutes. It's just like refueling your car. So Toyota and Honda are continuing on that path, whereas many other automotive companies are headed towards the battery solution. And just to point out that, you know, why do we use carbon fiber composites? I'm a material scientist, so I care about what materials these things are made out of. So you wouldn't use steel, for example, because its strength to weight ratio is really, really very low. So you don't have any of these steel tanks. It's either aluminum or carbon fiber composites. So hydrogen delivery exists already in some regards in the US. And about 90% of that is in the Gulf Coast region. And you recognize why, right? Because we make hydrogen from natural gas and we use it to do oil refining. So it's all in this area. And it's done using the pipelines are made out of high strength steel alloys. So that's 1,600 miles. The number of miles of natural gas pipelines dwarfs that, absolutely dwarfs that, you know, millions of miles. And this is that distribution system that exists already in the US. And so if you think about hydrogen delivery solutions, you could blend up to about 15% hydrogen into natural gas. But then you say, well, why did I do that? I'm not really eliminating the natural gas. I still have 85% there. Then you could think about replacing this with hydrogen-only pipelines. There's some benefits because the right-of-way is already established. And the real challenge here is that, okay, hydrogen needs to be at a higher pressure in order to deliver it. And it leaks through smaller pores than methane leaks. So it's at a high pressure and it's already a smaller molecule. So you have to change all of the connections. You have to change the compressors. And it's not clear whether or not you need to replace the pipelines. So this is really an area of study because hydrogen can embrittle steel. So that's where this billions of dollars of investment comes in, is because of this, you know, need to change these pipelines. Absolutely, we need to change the compressors and many of the components. And it's just not clear how many of the pipelines themselves need to be exchanged. So there is a case for using ammonia instead for the delivery of hydrogen. So I have, suspend disbelief. We're in Hollywood for the moment, which is accept that this reaction can be achieved, okay? Which is reacting hydrogen with nitrogen to make ammonia. This is the famed Haber-Bosch process, or not directly, but it's the Haber-Bosch process is well known because this is what created a lot of fertilizer for the US or the world and allowed improvements in agriculture. This is actually downhill at room temperature and atmospheric pressures. So that's why I can plausibly say suspend disbelief. Kinetically, it's a very, very difficult reaction, but thermodynamically, it is downhill. There are existing pipelines in the US, about 3,000 miles. And this happens largely from that Gulf Coast region where we have a lot of hydrogen, and there are, and natural gas as well. And there are these Haber-Bosch plants that make ammonia, and deliver it to the Midwest where we have a lot of farms. So that's why we have an existing pipeline, 3,000 miles. So that's actually more than the hydrogen pipelines, about twice as much, right? And what are the challenges here and the interesting things here? So at the same capital cost, this is analysis from Grigory Soloveichik, whose name I can never pronounce, but who used to be an ARPA-E program director, where this is a comparison to how much capacity there is for transmission of energy using electricity, using natural gas, and using liquid ammonia. And to liquefy ammonia, you have to cool it just a little bit or put it under just a little bit of pressure. So 7.5 times atmospheric pressure. So that's not a huge amount of pressure compared to even to the natural gas that is pressurized to 350 times. So huge advantage of using liquid ammonia. And then, what's called the protective zone. So you don't have to have a big right of way. It's very similar to natural gas. And so the transmission capacity then is very, very high. And the transmission losses, so this is the percentage loss per 1,000 kilometers. Historically, unfortunately, our electricity grid is AC, alternating current, as opposed to DC. It would have been much better had it been DC, but we didn't have converters to change from high voltage to low voltage back in the day. So there is this 3.5% transmission loss in our typical delivery system in our grid. And if you compare that to liquid ammonia, it is really very small. And so that's another advantage for using ammonia to deliver. Okay, and the case for energy storage using ammonia is that here's a tank for just putting it in the ground at a capital cost here of $100,000 for 200 megawatts. And if you were to compare that with batteries, here are just two examples. The cost is, many orders of magnitude larger. So that again is the reason to use these other carriers to store energy. So here's ammonia down here, so storage time. So it's almost infinite. There's actually, there's no reason why you couldn't store it forever. And hydrogen also, there's a little bit of leaks. So if you liquefy hydrogen also, there's boil off and things like that. So you can't really go for an infinite time with hydrogen, but you can go for many, many, many days and months. So people think about these chemical fuels as a way to do storage over seasons, for example, but you wouldn't use batteries for seasonal storage. We all know you take your laptop out after you haven't used it for a couple of days because maybe you were on vacation and you dared not to have your laptop with you, and you try to open it up and the battery is self-discharge, right? So that doesn't happen with the liquid fuels. Okay, so this is liquid organic carriers, but these are the ones that you have to recycle the CO2. So not great. So ammonia turns out to be really the winner here for what's called levelized cost of storage, means over the lifetime of the use of the technology. So that's what you get in terms of a revised sustainable energy cycle, is that you replace that hydrogen with ammonia, and now this becomes less costly. And the product then is nitrogen when you use the ammonia in your conversion device to get electricity. And we don't have to worry about recycling nitrogen because that's about 80% of air. That's great. Now, so again, ARPA-E had really pushed this. I realized in the past couple of years that many, many years ago when I started my academic career, some guy who I thought was completely nuts gave me his card and said, ammonia is the answer. Like, what are you talking about? But now, with all the excitement and the analysis of this problem, I get it. But the challenge with using ammonia directly as a fuel is that it is rather toxic. And it is corrosive, so you have to have really good stainless steels to be able to deliver it. although we have the experience, so we know, with those 3,000 miles, the US has that experience. But it means that you would probably want to do on-site conversion of that ammonia to hydrogen and put it in a hydrogen fuel cell for a vehicle to do that. So the hydrogen that you deliver to those polymer electrolyte membrane fuel cells has to be absolutely free of ammonia, because the ammonia, being a toxic agent, will also poison the catalyst of those polymer electrolyte membrane fuel cells. And it requires doing a high efficiency at small scale. So you need an electrochemical conversion device here. Okay, so I'll skip that and just say that in my laboratory, we've done lots and lots of things to try to address this, using fuel cell materials, using different types of electrolyte materials. We've done reversible cells that allow you to go back and forth between electric energy production and then hydrogen production when you have excess electricity. We've done this step of using ammonia plus electricity to make hydrogen. We've done even very high temperature ways of using solar energy to make hydrogen, but that, I think, again, is less compelling because now solar electricity and wind electricity are so much less expensive. And we're doing work on batteries for long duration storage and trying to do the ammonia synthesis, which is a very nascent effort in my group. I'm going to skip all of the technical stuff. Was way, way, way too much for this audience. All that great animation. But I'm going to leave you with one piece, which is to say, I'll just leave you with a little bit on the reversible cells that we can do here. So we're, taking solar energy in, or solar electricity in, and splitting water to make hydrogen. So this is the technology that we can use. So these are examples of the cells that we make. And then if you run it in the other direction, you are making the electricity. So this is downhill to make electricity, and then you're pumping it uphill to make hydrogen. And just to show you, this is our beautiful cells, but we can do the hydrogen production much better than anybody else. We can do the electricity generation much better than anyone else, and we can go back and forth. So it means that you really can use a device like this in a battery-like mode, so that you can, have fuel cell mode, battery mode, electrolysis mode, so that you're producing hydrogen, fuel cell mode, and back and forth. So it's like a battery, except that the electrochemical conversion piece is one side, and then you can have a huge storage container that is not limited by how many batteries you have. So that's the difference between using a reversible hydrogen cell as opposed to using a battery. Okay, so I'll just thank you for your attention, skip all of that, and thank my group for all the great work they do.
Great, thank you, Cecina. Come on over. Great talk, and thanks for mentioning the Haber-Bosch process. Some make the case that it's the most important thing humanity ever did, right? Not just because of the exciting energy applications, but because it feeds half the planet. So I have a question related to that, but let's take the audience questions first. Oh, there's a few. Let's start with Megan.
Either ammonia, I wonder if you could talk a little bit about either ammonia or hydrogen, if you're thinking about it as an industrial fuel rather than a transportation fuel, so you don't have to worry as much about transporting it to as many locations across the country. You don't have to worry about it being small cell. You don't have to worry about, average Joes knowing how to put it into their tank, things like that.
Yeah, absolutely. So you can absolutely think of ammonia as a fuel in those scenarios where you have trained personnel who are using it. I'm actually working with a small company to try to decide whether, for aviation applications, whether it makes sense to do a hydrogen fuel cell, whether it makes sense to do battery, whether it makes sense to do an ammonia fuel cell. So there are challenges. One of the challenges with ammonia, if you combust it, then you're going to get nitrous oxides. So that's a challenge. So that's why you want to use it in a fuel cell more so than in combustion. But in terms of industrial applications overall, I mean, you still, if you have your energy source far from where you want to use use that energy, then you have to decide how you're going to get it over there. So whether it's going to be the electricity that already exists at the grid, or whether it will be hydrogen, or whether it will be ammonia. You do have to think about the transmission of that. And there are energy losses through the grid. So it depends how far you need to go. Some of the industrial applications could directly use hydrogen for the processing, which is great. So you don't have to go through all these transformations. So I think there is a role, but unfortunately, it's one of those is sort of, it depends on the specifics. Yeah, so that's exactly it. Those scenarios, I think there is very much an opportunity to use it. Again, if you do hydrogen combustion with air, you do run into the challenge of making nitrous oxide because there's so much nitrogen in the air. We have technologies to get rid of that, but we just have to know that's an additional cost.
Yeah, thanks for that. It's not the nitrogen and the ammonia in that case. It's straight in the air, which makes it a bit more tricky. Great, go ahead.
Hi, thanks. This is a non-technical question because the numbers in equal signs, I don't even remotely understand the, I got the happy faces, but the rest of it was beyond me. But this is a question about what I sort of sensed was an undercurrent in your talk about how certain possible iterations of a transition away from fossil fuels and to clean and renewable energy are going to rely on the fossil fuel industry. And there was sort of, you made gestures towards how we may rely on or use actual existing physical pipelines, right, that may actually play a crucial role. I was shocked at the map that you showed of the pipeline map of the United States. I had no idea it was that extensive, but that might be something that we rely on. And I've been told by others that, there's also these sort of metaphorical pipelines from programs in engineering and physics into the fossil fuel industry. So there's sort of knowledge capture, right? There's a lot of very smart people who work for Exxon and Shell and BP and whatnot who are doing important work that's going to be very relevant to some of the developments that you're talking about. So I guess the question is, is the role for the fossil fuel industry not just sort of get out of the way and stop doing what you're doing, but is there sort of a necessary reliance on various parts of the fossil fuel industry for some clean energy developments?
Yeah, that's a very difficult question because certainly the fossil fuel industry has deep pockets. The total amount of R&D that fossil fuel companies do dwarfs any other industry sector or even government. And most of that R&D, as far as I can tell, is in finding new sources of oil, right? It's about how do you do deep ocean mine production and things like that. So shifting that knowledge towards efforts in other areas would be great. And again, I get nervous when the fossil fuel companies say that they're interested in hydrogen because we see what they do with the hydrogen. And similarly, when they say they're interested in CO2 capture, it helps pump petroleum more effectively because they push it down and that helps gets the oil back up. So, and many, I think, in the laboratory level researchers are interested in the science of it because it's just really fun and cool, and also do have the hope that it will benefit the transition. But some of the comments that were made earlier about I just do the research and I let someone else decide how it gets deployed. I think there's a lot of that. So the people who are truly making the decisions are not necessarily thinking about a sustainable future. I was in California when there was a proposition to charge the oil companies for extraction of oil, which many other states employ. So in Alaska, you get, if you're a citizen, you get a check because because of that fee. California has not had that historically. And the amount of money that the oil companies spent to defeat that proposition, it was more than the senatorial campaign. It was stunning. And so initially it was going to win, and then at the end they just convinced everybody that your price of gasoline at the pump is going to go up, and so people voted it down.
And just to follow up on Keith's point, do you think, say in the specific example you showed of the hydrogen pipeline that exists, and we know why it exists, but the 10th deployment of a technology is less expensive than the 9th, which is less expensive than the 8th, like the most expensive iteration of a new thing like a hydrogen pipeline is number 1.
Yeah.
Isn't it, can we celebrate a bit that somebody else paid for that, and now we can build on that?
Yeah, I mean, I think that is absolutely the case. So there's still this uncertainty as to whether or not those existing natural gas pipelines can be converted to hydrogen. If you had to change all the pipelines themselves, that $9 billion. I don't know. I mean, I'm not enough of a steel expert to understand why there's still debate on that. But it does seem there's debate.
Oh, well, we're being told hard stop, which is too bad because I've got more questions too. I guess I'll try to catch you at the break or at lunch. But we'll wrap up by this session by just saying thank you so much to our speakers. This has been fantastic. Thank you for coming.